of the nonlinear sigma model, which describes boson, Goldstone bosons, or Goldstone modes today. And it's way harder than the epsilon expansion that we did, and I'm going to try to do it all in one day. And today's that day. So I'm just reminding you what we are doing. We're starting from the same type of Landau theory, or Ginsburg-Landau-Wilson theory. And the only difference is that there's vector components. So these spins are n-component spins. And we've written them as a magnitude and a direction. And there's a constraint on the direction vector. It's a unit vector. So we use this to write the action in terms of rho and n. Like that. Which includes fluctuations in both the direction and the magnitude, and then the phi-4 term for the interaction. Okay, that's just by substituting in that decomposition of phi. And last time we looked at parallel and transverse components, talked about Goldstone modes. We argue for the existence of a lower critical dimension, which is d equals 2, which is the lowest dimension where the phase transition occurs. So that should be the lowest dimension where we expect some sort of non-trivial fixed point if we do the RG analysis of this. Okay, so what we're going to do is we're going to assume that we're near the lower critical dimension, which means that the magnitude of the order parameter, if you will, is basically fixed. So the rho part's fixed. And we're going to look at just fluctuations around that, continuous minimum of that potential. So I drew it before. So not like this. So we're going to assume that we're fixed into this minimum, which is the, ordering value of rho, or the mean field value, minus R over U. But we still have freedom in terms of this zero mode, or this fluctuation. So we're far below the mean field TC, that's what I'll call it. So that the magnitude so let's only keep fluctuations of the direction. And let's derive a different type of epsilon expansion, where epsilon is the distance from two dimensions. So let's say d equals 2 plus epsilon. And so epsilon is going to be the small parameter in the expansion. So it's like we're expanding around 2 dimensions. So we take our action, we rewrite it just in terms of the unit vector. What do we got? 1/2 rho. Seems easy, right? We only have one parameter now, so this rho. We can relate rho to somehow the, reduced temperature, if you will. So let's just measure rho in units of T, or vice versa. So I'm just going to redefine rho. I think I want rho squared. Yeah, I'm just going to put a T in front there. So. Or sometimes people call this K for the inverse temperature, or beta, right? So there's no 2 terms that you want to balance. So you just have an overall energy or temperature scale. So we're just going to define that as the temperature. And that's the parameter that's going to get renormalized. So, this looks simple on the surface. I can just write it as remember, it's x dependent, and n dot n equals 1. So you need that constraint. But that constraint makes things very highly nonlinear. So it means that in the functional integral, you have to always make sure that even though you're integrating over, all these direction fields in space, that you always keep that constraint. So. So the partition function, functional integral over n, that constraint is often written as a delta function, just n squared minus 1, and then e to the minus your action s of n. And that's called a nonlinear, because you'll see how nonlinear it is. Sigma model, nonlinear sigma model. Who's seen the nonlinear sigma model before? Right. Okay, so what we're going to do now is, assume an ordering direction like we did before. Remember we called it n or something? No. N was 1, 0, 0, 0, 0, and we had fluctuations in the field. So we're going to allow the fluctuations now, but we're going to subject it to this constraint. So that's your n components of your field, if you will, for your ON model. So we're assuming a ordering direction. And we'll call that primary ordering direction sigma, and everything else pi. Yeah, that's fine. And it's n components, so it has to be n minus 1 here. So there's one component that's special, that's the sigma. And then there's a vector of all the transverse components, if you want to call them that. Then that constraint, n squared equals 1. You can just write it as n squared, so it's this, plus a dot product, if you will. Let's write it like this. Okay, so then the constraint on all of these fields is just part of that nonlinear sigma model. So subject to that, we'll just write the action over n vector now is sigma pi vector. Oh, it's in real space. And I have this term. So the first component is just my sigmas. And my second term needs the rest of the elements in the dot product. So I'll just write it like this. Like that. And one thing about this constraint, which I'm going to use lots, is that, I mean, there's two solutions in principle, plus and minus. And I've thrown away that sign. So I'm assuming that sigma has the same sign everywhere. You know, as a, so this assumes. Okay, so it kind of makes sense if you think of, you know, low temperatures. You have a primary sort of ordering direction, and we're just considering small fluctuations or long wavelength fluctuations maybe around that ordering direction. Okay, so like off the top of your head, in these types of sort of long wavelength theories, seems fine. What it's neglecting is things like topological vortices, right? And I think the realization that, you know, what we're going to do today doesn't sort of cover all physical phenomena because of this assumption. That's one reason that, you know, Costas and Thales won the Nobel Prize. So. So we're going to cover that in a couple weeks. So what the nonlinear sigma model is going to show us is how, you know, I guess the long wavelength or the standard calculation for phase transitions and critical phenomena and fixed points goes. But just keep this in mind. Okay, so let's get rid of the sigma piece. We have a constraint here. Okay, let's solve for it. Let's write S just in terms of pi. So it's that first term squared. I'll just write it like this. Okay, I'm going to, okay, so things are highly nonlinear. So that's going to go into the action. I'm going to want to expand that in powers of pi at some point. But let's also write the, so we can write the full partition function. Let's rewrite the constraint here explicitly with a Jacobian. And then we've basically eliminated sigma also from this constraint. So I want, let's see, just the functional integral. So right, there's two functional integrals, and then delta sigma squared. So this is n squared plus pi squared, right? Okay, so you just need to use a trick. This delta function, I mean, I want to write it in a way that I have a functional integral and a delta function. So let me just sketch that out without doing every step. So I want to set up this nonlinear sigma model, and then the farther I get along, the more steps I'm going to skip. So otherwise, it'll take a month. So let me use this trick. So that I can write this type of delta function as a sum of two different delta functions. So then the functional integral gives me something like 1 over 2. My a is going to be pi squared minus 1 minus pi squared. Yeah. And then delta sigma plus a plus delta sigma minus a. And use those delta functions to do the sigma integral. So you got to do it in a functional integral sense, but this is nothing too crazy. So you can see how it'll give you something like 1 over 2. Oh yeah, and 1 for each of these. 1 plus 1, which gets rid of that factor of 2 there. Right, and further I can write this functional integral explicitly. So let me do that. So then it's d pi, so it's a functional integral, so it's a product over all I one minus pi I squared. See, because so the constraint, in a nonlinear sigma model, the constraint's everything. The constraint's what's giving you a functional integral in the fluctuations in the fields that we're interested in, which I've called pi. But it's not, it's a functional integral that has this extra piece of the measure, from the Jacobian. So then, that's product, that's big pi. That's a little pi. S pi. Right. So I'm just eliminating sigma now in the partition function. And what I want to do is I want to bring up this square root into the exponential, and that'll just give me an extra piece that it redefines my action. So it'll have some log root of this thing, and you got to be careful with the product. So there's my original S. Log of this thing, and it's a square root, so there's a 1/2 in front of it. Pi I squared. Something like that. And I'll just write it here. So let me write this as now my functional integral over pi. How did I write that before? E to the minus s pi. And let me turn that sum into an integral, which becomes strangely important later on. I'll just write it like that. So that a to the d, remember changing sum to an integral. It's just, let's see, n over v. That's a number of lattice points. That's the total volume. So those two pieces, I can rewrite a new Landau functional. Which is just S. Let's call it S. Yeah, I'm going to write it like this.
In the last step of the yellow equation, you bring the integration up, you basically just write out capital D pi, right? So pi is a vector, and we write it as the integration over each component. And
this integral's over.
I mean the yellow part.
Oh, this part here?
It's still pi. Yeah. So
I'm using this I for two different labels. So here I'm labeling it as overall this is all the fields. Yeah, and then all the components of the vector in that encapsulated in that vector sign here. So this is all fields. You have spatial position of all fields, and then you're taking the continuum limit here, making it so that field is just a continuous function.
So each pi still has n minus 1
Yeah.
components,
Yeah.
but those are different
Yeah.
vectors.
Yeah, I should have.
Okay.
I guess I'm putting the components for the pi vector as superscripts. So all I'm doing with this subscript is just motivating the fact that I have to integrate over all fields and spatially. Because every field is still a function of, it's a vector component and it's still a function of x. It doesn't get less confusing as we go on. Okay, I'm collecting all my pieces, but I forget what they are. Okay, so I should have a gradient. Oh yeah, so I'm up there. Okay. Yeah. So I have an integral. I don't know how to write this. I'll clarify all this when we start looking at it piece by piece. And t over 1 minus pi squared. Something like this. Mm-hmm. Okay, so I've just combined this. I've just put this inside the integral, this log, and factored out t. Looks right. Okay, so now what we do is we take this. So this is the definition, if you will, of the functional, or this action that we're going to perform the RG steps on. So we have to define an S prime, and we have to make that S prime equal to, you know, terms in the cumulant expansion, if you want. So there'd be a Gaussian term, then there's going to be a S1, an interacting term, an S int, I called it last time. Then there's going to be the second term in the cumulant. So the one thing that makes this nonlinear sigma model easier than the Ising model that we worked on previously was that we only need the first cumulant to get a non-trivial fixed point. Okay, so we don't have to do that. We don't have to do all those Feynman diagrams in the second cumulant. We only have to look at like one diagram or something like that. So we have to justify this as we go along. We're going to expand in terms of powers of that fluctuation. So you have to convince yourself that it's small. Remember, that's not always a justification that works out. And we're going to use that, you know, idea of expanding in powers of pi to get rid of the nonlinearity in these terms, or at least the functional dependence on the square root and the log. And then we're going to use the cumulant expansion to relate S prime to S. So we want to write, you know, S as something like Gaussian plus interacting, first cumulant interacting plus second cumulant interact, blah, blah, blah. So I'm just going to do these two terms. And then you got to integrate over fast modes and blah, 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 all that stuff, right? So we're doing all that today. So the Gaussian piece, which we won't have to handle, but just remember that it's there. Remember now, it's like in a low energy effective theory, not of the sort of microscopic spin degrees of freedom, but of the low energy excitations that correspond to, you know, moving around in that potential well minimum. So the non-interacting piece is a theory of non-interacting Goldstone modes, which is really what pi is. So non-interactions in that field. Right, and that one's simple. The only term we have is that. For the other two terms, let's expand and keep terms quadratic in the field then. And that'll give us S1. Okay, so we need something like this. So we have a 1 minus that thing, and we're taking the gradient of that, right? So you have to remember the gradient term. This is pi dot pi. So gradient gives us something like, gradient pi dot pi plus pi gradient. I don't know, something like that. So there's two of those, there's two terms, the dot product, and so it gets rid of that 1/2 there. Okay, so that goes into here. And we've got to square that thing. So we have the square of, two dot products. That's important. And then the log term's simpler. So for the log term, we're just expanding. What is it? 1 minus pi squared. Should just be minus pi squared. So that'll give me my first term, S1. And let me write this. So the square root turns into, what did I say, pi dot. Let's write this as pi squared. Looks simple. Okay, so you can do a dimensional analysis on this, and there's a t in this action here. So a dimensional analysis should give you somehow that the fluctuation, like the pi squared, the dimension of pi squared is going to be the dimension of t plus epsilon, or something like that. So I'm not going to do it. Something like, I don't know. So in some sense, we're expanding in orders of t. So S0 is order unity. S1 is order t, linear in t. So if you did the higher order term, it would be order t squared. We'll see that again. Okay, so now I just want to take this action. I'm not going to work on the Gaussian too hard. Well, I guess I can Fourier transform it. So I'll just write the Gaussian in k-space. We already know what that looks like. And then I want to Fourier transform this into k-space. And then look at the momentum shell. So then I'm going to take my pi's and constrain them into this momentum shell RG. So for every component, I'll do it. This defines pi a momentum k, say, e to the I k dot x. Okay, so this gives, this is the last time I'll write the Gaussian. That derivative squared, each one pulls down to k, remember? So that's why I have k squared, and then I can just write pi, let's see, k squared, where this thing, remember shorthand for, I would write it like k and pi, let's see, a, and minus k, which is constrained by the delta function.
Just going back a bit, I want to ask about the first yellow section. So just to make sure I'm getting this right, you're replacing the x with the square root of sigma squared plus pi squared, and a with 1?
I want a to be, a is this thing here.
Okay.
So it's sigma, so x is sigma. Because what you're doing is you're using that, delta function. So now you're taking an integral over a delta function, right? So you're doing this integral here somehow. So x equals sigma. Or sigma. Yeah. Other questions? Okay, so Gaussian piece, let's look at S1, the interacting piece. And what we're going for, again, is an RG equation, a recursion relation for this here, for inverse temperature, or the K coupling, some people call it. And even, I think on your assignment, I've actually given you this RG equation for 2 dimensions. So we're hoping to get a fixed point. We're hoping to get a fixed point that's epsilon away from Gaussian, where epsilon's the distance from 2 dimensions now. And it's going to come from this S1 term. So after the Fourier transform, let's see, we have to keep track of all this. So I'll just write it once. So d dx so you Fourier transform every field with a separate k, remember? And then you constrain them by your delta functions. Okay, I'm not going to write that many more times. This term here pulls down, when you take a Fourier transform, it pulls down a k, remember? So I have 4 fields, K1, K2, K3, K4, and they each have to have separate labels, and 2 of those fields, because of this grading term, pull down a k in the Fourier transform. So the way I've written it, you could write those, the k, say 2 or k2 from the first instance, and k, say 4. Is that what I did? No, I wrote them as K1 and K3. Okay, so that's the two momentum coming from that term. So K1 dot K3. Then you have your 4 fields. Just got to keep track of which ones are which. So like I said, there's 2 coming from each term in that square. And they have to have the same, right? You've taken the dot product, so you have to have the same components. So that's for one of these squares here. Right, so that's one dot product. But then you need the other one, but that's a different index in principle. Right, because they're not related. They're just 2 scalars that you've multiplied. So you need a b here. We have 4. Right, and so you need 1k here from each. So yeah, you have k1, and then you have k3. And that's the 2 grad terms. Okay. Well, I need the Fourier transform, so e to the I k x dot k1 plus 2 plus 3 plus 4. We'll get rid of that in a minute. You've seen that term before. Now I need the piece that came from the log. Right, so the pi squared piece there. There's only 2 fields. So I just use the delta function to constrain the fields to be plus and minus k as usual. So again, this term comes from the measure. And in principle, you can not consider that term. It has to do with the fact that you have this a to the d here. I'm gonna keep it in just so we can see how the Hamiltonian or the action is self-similar after an RG transformation. But the important piece where the non-trivial recursion relations come from is this piece here. So there's, let me call this piece the easy piece. This piece is the hard piece. So we have the Gaussian piece, S naught. We have an easy piece, and then we have the hard piece. Okay, so just like before, now you can do an RG coarse graining. You have this momentum space. You do the coarse graining in momentum space. You take the momenta and split them into fast and slow modes, and you integrate over the shell. Yep.
That was the decay green and the 2.5D, should that be the decay 4?
Yeah.
We're not unpacking roots.
You can use a delta function to get rid of that, but yeah, four fields, 4 Fourier transforms. I ran out of space. Well, let me just note then that, let me get rid of that delta function. We usually do that delta function integral. And remember, it gives you an extra 2 pi. That's important for constraining the momenta, right? They're not all independent. That's the whole trick with all this stuff, is to understand how these delta functions relate to momenta. Okay, so now let's do the RG. Split into fast and slow modes. where for every component, for every momentum, slow plus fast. And remember, the fields are only defined within their respective shells. So we have a cutoff capital lambda. And then we have a lambda over b. And the slow modes are only defined in here. And the fast modes are only defined in here. Oh, I have another board here. I'll use this one. Good. Okay, so we have to write all these terms out. Remember, what we're doing is, in analogy to the first, remember this is the argument of an action. We have the partition function, so e to that action. Remember, we have the cumulant expansion and all this stuff, so. What we're trying to define is a coarse-grained action after one RG step. And that'll only depend on the slow fields because we're going to integrate out, remember, we're going to integrate out that shell. And after we define this, then we rescale x prime x over b, or k prime equals kb, and we renormalize the field to get us a new pi. So again, there's the slow piece from the Gaussian, and then we need the expectation value of the fast piece, which depends on both the interacting piece, which depends on both slow and fast, so it's a Gaussian integral, remember, and it's over fast modes, and we'll ignore higher order terms. So what we need to do is basically average over, we have to do this average and put it inside the integrals. So we know how to do the Gaussian piece. I won't do that again. So let's look at S1. Okay, let me look at, actually what did I call it? S1 easy. That looks the same as a Gaussian piece, basically. Except you can mix fast and slow fields. But we know how this works. So we take that field, if you want, split it into fast and slow. And then we get terms that are like, I don't know. Averages over I don't know why I'm doing this. I said I wouldn't, but we get terms that look like slow fields, Gaussian pieces, and then we also get, just to remind you, expectation values over fast fields, right? I'm not going to do them. I'll just write them in real space. And those terms are additive constants. And there's no cross terms. There's no slow times fast, because the integrals are defined such that by symmetry those are 0. Okay, so even though that occurred in S1, it's trivial. You just got to keep track of the prefactor 1 over a to the d. That somehow becomes important. So let's look at the hard piece, the first term up there. I don't know if that's the right name for it, but so now I'm looking at this whole piece here. Hard. And you need to keep track of all these terms. So I have this delta function over 4 momenta. I have my k1.k3, which is kind of the important new ingredient. And then I have all these, I think I called them A, B, C, D, E's. So those are all the possible combinations of slow and fast fields. Okay, so now I'm going to start to get real spotty in my derivation. So A looked like all slow fields. We have to actually keep this one. So we have slow A, K1, slow A, K2. And I can keep track my separate A's and B's. Slow. So that term will renormalize like the 5-4 piece in some sense. Remember that term gives us renormalization in what we were calling U at some point. Here it's all mixed up because we've done these expansions, but it'll renormalize the first part of this type of integral. And then we have terms that are, we had A, B, C, D, E, so this was all slow fields. I wrote it down. So B was all fast fields. So it's like this piece here. It's a sum over, it's the expectation, it'll give you the expectation value of something that's all fast. So it's like those parts of the free energy that, in principle, if you want to have the exact RG transformation, you keep, but you end up dropping them because they don't affect, any derivatives of the free energy. So they don't affect the physical estimators. C and E were odd. And I forget if I made you prove this or not, but by Wick's theorem, then these terms are all 0. So I need the one that's D, which is too slow and too fast. So it's like slow, slow, fast, fast. So that'll give us you have a question?
Yeah, please. There's unbalanced parentheses in that thing that you boxed. Are you missing a square or something?
Oh. Yeah. Let's go here. Yeah, it's probably like this. Yeah. Yep. I'm not even sure that's really an equation anymore there. I'm just just telling you what it'll look like. This is also not an equation. I'm just going to argue for which terms are included and which ones aren't. So it gets sketchier. So really, you have to. This is a little tricky because you have different indices on these things. Like, should this be A, B, or should this be AA, BB? And then what about the fields? K1, K2, K3, K4. So you have to think about that, and all those K1, K2, K3, K4 also affect that. Where's that term? This matters here, right? Because if these are fast fields, they have to be in the fast integral. And if they're slow, they have to be in the slow integral. So you get all these constraints on which terms matter. There was 6 in the original Ising. So if you look at the diagrams and the constraints from the delta function and the combinatorial pieces, are actually 6 possible terms. But the only terms that matter are basically 2. So I'm just going to tell you how you do this without doing it. So there's a symmetry. So first off, I guess it's probably the only important one. You need both of these labels, 1 and 3, to be either fast or either slow, so that the corresponding integral is even and not odd. And if it's odd, it integrates to 0. By writing the integral. So it's the integral over fast modes. So you have to do an integral over fast modes. You have an odd mode in there, and you're integrating, you're doing that full momentum shell. So by symmetry, it'll just go to 0. I'm just trusting something Anton told me, so I assume that this is correct. But if it's not, then we're in deep trouble. Or let's see, what is the statement? It's the fast integrals are odd. Odd, and they go to 0. Not very convincing, I agree. It's worth writing it out if you want. So if we assume that that's correct, then there's just 2 cases, one where they're both fast, one where they're both slow. So let's look at the both fast case first. Both fast, the S1 first term, or hard term, gives okay. So it's this one's fast, this one's fast. I need the expectation value of 1 and 3. Right, so it's A and B. That makes sense. K1 and 3. And then these are my slows. A, 2, B, 4. So when I do the momentum shell, then this one, then I'll have an even term when I integrate over the shell. So we need that expectation value. Remember how this works? This is like our G naught, our Gaussian expectation value. So just in general, we haven't calculated that thing specifically for these types of fields. So we need, I'm going to call it the 2-point function. Very generally, Q and Q prime. And we need the Gaussian expectation value of that. And here the fields are both fast, so this is taken care of. So we just need that Gaussian integral. So you can do it. Turns out that you need the same field components. So you need to get a delta function there. There's a T that looks different than the Ising model, but then the rest is pretty much the same. So constraints are Q and your Q prime. Okay, so this is like the equivalent of your Gaussian propagator here. You might call this G naught Q. Yeah. Okay, so it looks massless. There's no mass piece in there. This gives a delta function. You also have this delta function. It's the same two kind of delta functions we had before. So let me call K1. So this is the same. K1 is minus K3. Okay, from this delta function. So whatever, let me call K1 dot K3. One's minus is minus K squared. Oops, minus K squared. I'm going to call that Q. I'm going to call that minus Q squared. Minus Q squared. Because it's like this Q here. And then the other delta function, we have, we have 4 fields, but now we've constrained 2 of them. So this gives me K1 and K3 cancel. So K2 plus K4 have to equal 0. Let me just call that K. So now I have Q and K. I can't remember if that's what I used last time. Q is fast and K is slow or something. Okay, so S1, what was I calling hard? Both fast. So now I have my slow modes. I'll write it like this over K. and my fast modes. So my shell. Okay, so this is where you would see the even versus odd. So if you only had one slow and one fast, then you'd only have one Q in here. So then you have to argue that that's 0. So we need this. We got to do this integral. But we do these lots. Remember, so this is one of the D terms. We need the both slow. And then in the RG, we also need the A term. So the both fast has this integral. And we see in the both slow, all that happens is this Q moves into the, turns into a K squared, right? So that's the only difference between fast and slow. Let me just write that down. Moves into the slow integral as, say, K squared. So it just moves into here. So you see, you can imagine doing this, right? It makes sense. We need those integrals. So for each case, we need an integral. So let me do the fast case first, which will be, we've done these before. We have to integrate that propagator. Which one am I doing here? Okay, that's one for the slow. So all we do is pull out the surface area, integrate, and it's Q to the D minus 1. And that propagator G is T over Q squared. And we can also use, which we will later, to write in differential form. B is e to the delta L, which implies that this thing, I1, is just S dt. Oh. Pi to the D. That'll cancel. I'll get this piece factors out, D minus 2, and delta L. I stand by that. So in the case when Q squared is not in the fast integral, oh, that's that case. In the other case, we have the Q squared, so I'll call that I2. Same thing. This is where something crazy happens. So this q squared cancels the 1 over q squared in the propagator. So all you're doing is integrating, this thing here. All that is like 1 over a to the d, right? We always use that when we substitute between, I don't know, continuum and integral or something like that. So all you're doing is, all that integral is 1 over the, the volume, the discretized volume in K space. So any term that has that integral, so I guess it's that, okay, both fast or both slow, both fast. That basically doesn't do anything in some sense. It just gives you a trivial renormalization. So up to the redefinition of the integration bounds. So basically, it's like this piece here is, where's my t? Oh, here it is. So this is like t times, d, dd, sorry. Something like that, right? So that's just something like t to the 1 over a to the d. So that piece it'll really just renormalize the thing I was calling the easy piece, S1 easy up there. So in principle, those two terms cancel. I mean, but if you want the S to be self-similar, you just want to see how that cancellation works. So all you're really doing is renormalizing by like something like this, which just means you're counting the amount that you're coarse graining. It's just like that term just counts a number of points. So that's kind of lucky. So the only piece we have to worry about is that I1. So let me write that down. So let me write I1. I mean, there's a t in here. This t is the thing we want to keep track of. So I could write this as some function of b, id to the b maybe. I guess it's really this step so that's just I1. So let's pull that t out, because now let's just collect all the terms. And you just got to keep track of what they all are. So in some sense, it's easier than the Ising calculation because we've only done the first cumulant. Remember in the first cumulant in the Ising case, you didn't have a non-trivial fixed point. So we're just hoping that we do here. But we can already see where this is going to come from because there's a non-trivial renormalization of t that comes from, okay, I better write it, or it won't make sense. The combination of S naught and that both slow. So where's S naught? Oh, I just erased it, right? Okay. So that Gaussian term plus, the S1 fast fields, this is what we're writing. So here's the Gaussian piece. And then, is it both fast or both slow? I think it's both slow. So I'm going to call it T I to the D, which is a function of B. And then this will just give me a piece like that. So that's Gaussian, S naught. This is both slow, right? So S1 renormalizes S naught. So that didn't happen before in the Ising case. And nothing else matters. So we get a piece that's like, from what I call the easy piece that came from the logarithm, and then both fast. Looks like this. And they both have this term here. So that's S1 easy. Sorry, I'm just naming these on the fly. And then this one was both fast. God. That's that piece there. That's it? Oh no, the fields. I forgot the fields. And then, what do we forget? What's the other term? Both fast, both slow. We have a piece that came from the log. We have a Gaussian piece. There's one more thing you need to make it self-similar. That's the A term. Right, the A term over there is just all, that one up there, it's just all the slow fields, right? And that, again, that'll just give you a trivial renormalization. And then you could Fourier transform this back. It's important to keep track of the A and B indices while you're in K space. 1, 2, 3, 4, and K1 dot K3. Right? So that's the A piece. Now what do? You rescale and renormalize. Rescaling means taking the K to B, K prime, what is B times K? So that's your coarse-grained Hamiltonian. So what you do is you rescale, which means K prime equals BK. And renormalize, which is the field. So this one you need to know the scaling dimension, Z, pi, and you're renormalizing the slow fields. So it's like you're taking that shell and you're moving it, you're taking that inner shell and you're rescaling and renormalizing it so that it's the full K space again. Is this the same Z as for the Ising field? Remember the scaling dimension for the Ising field? We calculated this. What do you think? Of course not. It's way harder to calculate. It's like an assignment 5 question. Not the Ising scaling dimension. So that sucks. Otherwise, we're done. So let's just leave it as Z for right now. So I'll just write the full S prime. So I have a K. Man, this is going to be complicated. So I have a 1 over T, 1 plus T I D. Is that right? Yeah, okay. Now I got to keep track of all my, okay, so I have b to the minus d, and also b to the minus 2. Is this right? And then I have a z squared from the fields. d dk. Now prime, yep, 2 pi d. I have my k squared, so it's now k prime squared. That's where this minus 2 comes from. K prime squared, pi, k prime, pi, k minus k prime. And you can work out, you know, the for the other two terms, the rescaling plus renormalization, plus two terms that renormalize trivially. The first one is just renormalizing in the density of points. The second one actually looks different if you put in the scale factors, but it's only different up to order t squared. Up to order. And we've just done the expansion out to order t. So yeah, it's just like before. It generates higher order terms, like phi 6, remember we generated before? So this term does generate higher order terms, but we'll drop them for the same reasons. They're irrelevant. So the RG equation just comes from this piece here. And remember, again, that's what the problem with the Ising model is. We didn't have a non-trivial fixed point in the first order cumulant. So let me write it like this. That integral's in there, I1. Let me write it like this. B to D. So then I have 2 pulled out. D minus 2. And if I write it like that, then probably, wait, I forgot something. A square. That's enough to give you the wave function renormalization. So we can solve for z over b to the d. It's a little tricky. You have to keep the constraints in mind. But this actually gives you the most important piece of the RG equations, the n. So I think it's worth doing explicitly. I1. Okay, so that should be seared into your brain if you struggle over it enough in the assignment anyway. Okay, so that's it. That's all you need. And the RG equation then which again gives us the fixed points and everything. Looks like this. Let me square that. So it looked like this. I think. And let me use this equation for I1 in terms of, oh yeah, let me use this equation here. In terms of delta L. So okay, so I1, what's the story with I1? I want to write this in terms of epsilon. So if I b to the d minus 2, that's equal to e to the d minus 2 delta L, right? And you expand this out. So it's 1 plus, and let me call that epsilon, delta L, where epsilon is equal to d minus 2. Yeah, that'll work. So then my b here, 1 plus epsilon delta L, 1 minus n minus 2. Let me write that I1 so I can pull out, okay, so I have that to the epsilon, 2 pi to the d. I want to pull out that delta t, or sorry, that t and that delta L. So let me just write it up to that order. Yeah. Then let me only keep terms linear in epsilon and linear in delta L. The epsilon's no problem. And then delta L plus terms that are higher order in delta L. And just move over to this board. So, actually that's pretty good. If I just redefine my temperature to pull a cutoff in there, and get rid of that annoying 2 pi over d, then my differential equation should be something like epsilon minus n by 2 t kd or something like that. Okay, we'll talk about this next time, but that's the recursion relation. That should be the RG flow equation for the nonlinear sigma model. So if epsilon's not equal to 2, there's some it's non-trivial in terms of its solution and so on. So you can already see something special happening at d equals 2, n equals 2. Subject to the caveat that you actually solve the wave function renormalization, which is where that n comes from. But this is the equation that basically leads to the Cosworth-Saldus transition temperature and so on when both of these terms are 0. There, I knew I could do it in one class. I just had to skip all the hard steps. So we're going to take next week off for the March meeting. So when we come back after next week, the Wednesday after, I'm going to look at these RG equations. I'm going to look at the fixed point. I think on your assignment, you've set epsilon equal to 0, and you're looking at that temperature. And if you had a field, you would have another one for the field, right? So you're looking at that in your assignment now. We're going to look at this fixed point a bit in class, and then I'm going to use it to motivate the special case of O2 2D, which is when we have to include, negative values and vortices and so on in the spin configurations. Negative values in sigma is what I meant. Okay, questions on this?
For the integral for I2, that meant to be from sigma would be to, lambda would be to lambda?
Oh, yeah. That's weird. That's a weird one. Yeah. Yeah, this is lambda. It's the same integral with the q squared in it. That's all it is. But yeah, it gives you this like weird, fact that it's equal to, the only difference is this piece here. And that's something that doesn't matter for the RG. But I1, this is I1. I1 occurs in these expressions only. There's no I2. So I1's the integral that matters in all these expressions. And that's what I substituted in here, was I1. Other questions? Okay, so I'll see you guys not next week, but the week after.